This is a video from section 3.2 in a linear algebra class. Let's take a look at theorem 3.2.3. If u, v, and w are vectors in Rn, and if k is a scalar, then A, the dot product of the zero vector in v is the same as the dot product of v and the zero vector, which is equal to 0. B, so I'm going to take the dot product of u plus v with w. That's equal to the dot product of u and w plus the dot product of v and w. So that's part B. Part C, u dotted with v minus w is the same as u dot v minus u dot w. Part D, u minus v dotted with w is the same as u dotted with w minus v dotted with w. Part E, k times the dot product of u and v is the same as the dot product of u and kv. So what we're going to do from here is look at the proofs. So in part A, we want to show that the dot product of the zero vector in v is the same as the dot product of v and the zero vector, which is equal to 0. So remember, v is a vector in Rn, and by context, the zero vector is a vector in Rn also. So we're going to let v equal the vector v1, v2 through vn. And we're going to let zero vector equal, now this is a vector where all the components of the vector are 0. And there are n components where they're all 0. And that's right here. And so we're going to brute force part A. So let's take a look at the dot product of 0 with v. And so that's 0, 0 all the way through, dotted with v1, v2 through vn. That's equal to 0, v1 plus 0, v2 plus all the way through until 0, vn. That's equal to 0 plus 0 plus dot, 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 plus 0. And that's equal to 0. So that tells me that the dot product of the zero vector in v is 0. And you can see by a very similar argument, we can say that the dot product of v with the zero vector is also 0. So I just go in reverse. And so what we can say from here is that the dot product of the zero vector with v is the same as the dot product of v and the zero vector, and that's equal to 0. Part B, we want to show that the quantity u plus v dotted with w is the same as u dot w plus v dot w. So we're going to start with the left-hand side. So the quantity u plus v dotted with w is the same as w dotted with u plus v, the quantity. And that's symmetry. But that's equal to the w dotted with u plus w dotted with v. That's the distributive property. But that's equal to u dot w plus v dot w. That's symmetry. And the last line just basically says the result has been proven. That's part B. Let's take a look at part C. So we want to show that u dotted with v minus w is u dotted with v minus u dotted with w. So one thing I want you to realize is that v minus w is v plus negative w by definition. And so I'm going to take the dot product of u with v minus w. But that's equal to the dot product of u with v plus negative w. But I know the distributive property works when there's a plus, right? And so this is u dotted with v plus u dotted with negative w, right? That's the distributive property. But remember, negative w is the same as negative 1w. And that's what I'm putting here. And so this is u dotted with v plus u dotted with negative 1w. But by symmetry, we can say that this is u dotted with v plus negative 1w dotted with u. So again, that's symmetry. Now, this negative 1 here is constant, and we can pull that out, right? And so this is u dotted with v plus negative 1 times w dot u. So there's a result that allows us to do that. Now, we can say that this is u dotted with v minus w dotted with u, and by symmetry, this is equal to u dotted with v minus u dotted with w. And the result's been proven. Part D. Once we establish C, D is much, much easier. So in part D, we want to show that u minus v, that quantity dotted with w, is u dotted with w minus v dotted with w. So we're going to start with the left-hand side and basically show that we're going to get the right-hand side. So what I'm going to do is take u minus v dotted with w. But by symmetry, this is w dotted with u minus v. Part C tells me I could write this as w dotted with u minus w dotted with v. But this is equal to u dotted with w minus v dotted with w. So that last line here is symmetry. And we've proven the result. So u minus v, that quantity dotted with w, is u dotted with w minus v dotted with w. Part E. We're going to show that k times the dot product of u and v is the same as the dot product of u with kv. So start with the left side. K times the dot product of u and v. By symmetry, this is equal to k times the dot product of v and u. That's here. But this is kv dotted with u, and there's a theorem in the book that allows this. So we have to show when k is here, we can pull it out in front. We only know what happens is when k is being multiplied by u. But what happens when k is being multiplied by v? And that's what's going on here. We have to justify this. But by symmetry, this is equal to u dotted with kv. And we're done. K times u dot v is the same as u dotted with kv. And that'll conclude this theorem for section 3.2, and we proved a theorem. Thank you.